We will now be looking at the Poincare transformation and its consequences for quantum mechanics in some more detail. Recall that the Poincare transformation essentially is this transformation where space-time coordinates of one frame go over to space-time coordinates of another frame. X prime mu is given by lambda mu nu x nu, of course a sum over nu is implied here, plus a mu. And these lambda mu nu, these constant coefficients, obey the standard demand for Lorentz transformation matrix elements. Eta mu nu lambda mu rho lambda nu sigma is eta rho sigma. Now corresponding to this transformation, there is going to be a transformation in rays. On the rays describing a quantum system. T lambda comma A is a transformation which changes rays into rays. But as Wigner's theorem has told us, corresponding to every such transformation of rays, we can find an operator which acts on vectors belonging to those rays, and gives you vectors belonging to the new ray. So this is the transformation psi going over to u lambda comma a psi. And according to Wigner's theorem, this u could be either unitary and linear or anti-unitary and antilinear. But because Poincare transformations are obviously connected continuously to the identity, we know that they have to be unitary. Now the way in which Poincare transformations compose has been worked out earlier, and the simple consequence is T lambda bar T lambda A, which remember means do lambda A first, then you do lambda bar A bar, is the same as a transformation with parameters lambda bar lambda and lambda bar A plus A bar. Because our unitary operators are supposed to mimic that, what we are claiming is that they obey u lambda bar A bar times u lambda A equals u lambda bar lambda comma lambda bar A plus A bar. Let me just remind you here that according to quantum mechanics, the fact that the states are really represented by rays and not by vectors tells you that you could have a phase factor inserted into this relation, and that would actually mean that you do not really have a representation as we are claiming here, but you have a representation up to a phase, or what is technically called a projective representation. We will come back to the issue of projective representations later. For the time being, I am going to assume that the operators which act on the Hilbert space furnish a representation, a genuine representation. That is, there is no extra phase factor to worry about. Now, much of the information about any such continuous symmetric group is encoded, as we have seen earlier, in the group elements which are very, very close to the identity. So what we are going to do next is take a look at the Poincare transformations when you are very close to doing nothing. Now, if you actually were to do nothing, the parameters that you would get would be lambda mu nu equals delta mu nu and a mu, of course, equal to 0. Just as a quick check, under this bunch of parameters, x prime mu will be delta mu nu x mu plus 0, and that's just x mu. You have done nothing, so the coordinates haven't changed. Now, if you were to change slightly from here, you would get an infinitesimal transformation, and then lambda mu nu will differ infinitesimally from delta mu nu. So you will have a very tiny correction term for each of the lambda mu nu's. Let's call them omega mu nu. Similarly, a mu will differ only very slightly from 0. So let's call this epsilon mu. Epsilon being the standard symbol for tiny change everywhere in calculus. So when I'm calling the translation parameter A, I would usually mean a finite translation. And when I'm denoting that by epsilon, I'm implying that there is a very tiny translation. So epsilon is a infinitesimally small number, or at least a very, very small number. The same, of course, goes for omega mu nu. Now, on the face of it, there are 16 omega mu nus, simply because mu and nu each can take 4 values, 0, 1, 2 and 3. And there are 4 epsilon mu's. So it looks like you have 20 infinitesimal parameters to work with. However, that's not quite true, because while epsilon mu's are arbitrary, apart from being infinitesimal that is, there is a restriction on omega mu nus. And that restriction, of course, comes from the fact that lambda mu nus cannot just be arbitrary numbers, they have to obey the basic relationship. Eta mu nu lambda mu rho lambda nu sigma equals eta rho sigma. So, eta mu nu lambda mu rho, instead of lambda mu rho, you'll have to now write delta mu rho plus omega mu rho times lambda nu sigma this has to be equal to eta rho sigma. A word about my handwritten typography here. I have been careful to separate the nu and sigma indices. The order here matters. Nu is the first index, sigma is the second index. I have not really been that careful about the indices on delta, although I have shown nu as the first, sigma as the second here, but the gap is a lot less, and frankly I could have just as well written it as delta nu sigma, for the simple reason that delta is symmetric in nu and sigma, so it does not really matter for delta which is first, which is second. As you will soon see, it does matter quite a deal in omega. Which index is first, which index is second, which is the row index, which is the column index, so to speak, in terms of matrix language. That makes a difference for omega. And that we will see soon, because all I have to do to see that is expand this expression out, remembering that the expression for lambda has been written only up to first order in omega. So, if omega were finite, there would be higher order correction terms. This is just a first order term. So, any algebra we do this will be consistent only if we keep up to first order. Pushing it beyond first order would be mathematically wrong. So, when I expand out the left hand side of this expression written in red now, I will get 4 terms nominally, but out of them one term has 2 omegas in it multiplied together, and that term is second order, so we will just ignore that. So let's look at what we get if we look at the other 3 terms. Well, eta mu nu, delta mu rho, delta nu sigma is one such term. Another term is eta mu nu, delta mu rho, omega nu sigma, that is, I am taking the delta from here, omega from here. And the third possibility, of course, is that I can take omega from the first bracket, omega mu rho, and delta from the second bracket. And as I have just said, the fourth term will have 2 omegas, so we will just ignore that. And this, of course, has to be eta rho sigma. Now, the very first term that we have here, eta mu nu, delta mu rho, delta nu sigma, is being summed up over mu and nu. And the simple rule when you are summing up something using a delta symbol is the summation index goes away and everywhere else is replaced by the other index. So here, for example, delta mu rho, eta mu nu will essentially change this mu, the mu on the eta to rho, and delta nu sigma will change the nu to sigma. So you have eta rho sigma on the left. Now that is not surprising, because if omega were 0, which is if these 2 terms were absent, you would definitely have eta rho sigma on both sides. Now what about the next term? This is eta rho nu, omega nu sigma. And this term, again using the delta symbol, is eta mu sigma omega mu rho. And this is equal to eta rho sigma, which of course cancels from both sides. So we are left with eta rho nu omega nu sigma plus eta mu sigma omega mu rho equals 0. Now, the job of the eta, the Minkowski metric, is to lower indices. Eta rho nu omega nu sigma would lower the nu index and make it into rho. And eta mu sigma here would lower the mu index, make it into sigma. So what we get once we carry out the lowering is the following. This term becomes omega rho sigma, and this term here becomes omega sigma rho. And as we have already seen, the sum is 0. So what does this tell me? It tells me that when you write omega with lower indices, once you have lowered both the indices of omega, the omegas are antisymmetric in the interchange of sigma and rho. So all the omegas are not independent. If you know omega 1, 2, for example, omega 2, 1 is just the negative of that. Omega 0, 0, for example, has to be 0 because this equation is telling you omega 0, 0 plus omega 0, 0 equals 0. Not only omega 0, 0, all diagonal omegas have to be 0. So let's now do a quick count of how many independent omegas you have. Without this constraint, you would have had 16 omegas. Now, once you have thrown in this constraint, you get 4 of them, the diagonal ones, to be 0 anyway. So you are left with 16 minus 4 equals 12 omegas. But out of the 12, if you know one half of them, let's say you know omega 0, 1, omega 1, 2, etc. The other half, omega 1, 0, omega 2, 1, automatically follows by just appending a minus sign. So there are actually 6 independent omegas. So there are 6 parameters which talk about the Lorentz group part of this transformation. In addition to that, in the Poincare group, we have translations. The 4 translations can be chosen completely independently. So you have plus 4 independent epsilons. So the Poincare group is described by 10 parameters. Right now we are infinitesimally close to the identity, and we can say that there are 10 distinct parameters which talk about different Poincare group elements infinitesimally close to the identity. And that of course means that you are going to get 10 generators or Hermitian operators which describe what the unitary operator looks like when you are very close to the identity. Okay, just one word of warning here. We have said that the omegas are antisymmetric in rho and sigma. And that's of course right. But remember, that's when the omegas have lower indices. So, just to be careful, let me indicate to you how this works out for the original omegas which were sitting in the lambda matrices. Remember, they were omega upper mu lower mu. And this antisymmetry is about lower index omegas. So, for example, omega 0, 1 is minus omega 1, 0. That follows from the antisymmetry. But what about omega 0, 1? Now, remember, Weinberg uses the metric eta 0, 0 equals minus 1, eta 1, 1 equals eta 2, 2 equals eta 3, 3 equals plus 1. Let me warn you once again that most relativistic quantum mechanics books or field theory books actually do not use this metric. They use eta 0, 0 equal to plus 1, eta 1, 1, 2, 2, 3, 3 equals minus 1. So when you're reading Weinberg and comparing his results with some other textbook, you have to be careful about this distinction. Anyway, according to Weinberg's metric, omega 0, 1, when you're raising this index, By the way, raising is done not by eta lower 0, 0, but by eta upper 0, 0, the inverse. But eta is self-inverse, so the numbers are the same. Omega upper 0, lower 1, which you get by raising the 0 index, happens at the expense of a minus sign. So it's minus omega 0, 1. The minus sign comes from eta upper 0, 0 being minus 1. Now, this of course is the same as omega 1, 0. Two minuses make a plus. And now let's try raising the 1 index. You're going to end up with no change of sign, because remember eta 1, 1 is what goes in there. Eta upper 1, 1 of course, and that's plus 1. So the antisymmetry, omega 0, 1 being negative of minus omega 1, 0, works for lower index versions, does not always work for the original omegas. On the other hand, if we were to look at, say, omega 1, 2, then omega upper 1, lower 2 is actually the same as omega 1, 2 with both index downstairs, simply because you have to lower using eta 1, 1 here, and eta 1, 1 is plus 1. Of course, this means that this is minus omega 2, 1, and hence, by raising the 2 index again without any change of sign, we end up with minus omega 2, 1. So, in some cases, for the original coefficients, you are going to get a change of sign if you interchange the 2 indices. In some cases, you won't. It's pretty easy to figure out when you will and when you won't. If both indices happen to be spatial indices, then you will have a change of sign. If one of them is a temporal index and the other one is a spatial index, then you are going to get the same value if you were to interchange the 2 indices. I am talking here, of course, of the original mixed index version. When both indices are downstairs, then you have antisymmetry. So this is something you have to bear in mind. With this background, let us take a look at the form which the unitary operator u lambda a takes when lambda and a are infinitesimal transformations. So, in what is going to come, I am going to write an infinitesimal Lorentz transformation with lambda equals I plus omega and a equals epsilon. So this is going to be how I denote an infinitesimal transformation. This omega, of course, is a matrix with omega mu nu as elements, and epsilon is a column vector with epsilon mu as components. Now, if I just look at this, lambda equal to identity, of course a 4 by 4 identity, and a equals 0. This is the identity Poincare transformation doing nothing. The corresponding operator, unitary operator on Hilbert space, might actually have a phase, but that phase would be independent of the state which it acts upon. The argument is very similar to the argument that we gave earlier about why ut1, ut2 could be equal to the I phi ut1, t2. But there, we have to bear in mind that the phi does not depend on the state on which this operator product is acting. By a very similar argument, you can show that ui0 can have a phase times the identity, but that phase would be exactly the same for all states, and you could absorb that phase in the definition of the state itself. Remember, a state times a pure phase belongs to the same ray, so you will not be changing any physics if you were to just change every state by that phase factor. And by doing that, you will end up with ui0 being represented by the identity. We are going to assume that that is always being done, so that the identity Poincare transformation is represented by the identity operator. Now the question is, what is the form of the operator when you have an infinitesimal Lorentz transformation That is, lambda is I plus omega and A is epsilon. Of course, this is going to deviate from the identity by an infinitesimal amount parameterized by omega and epsilon. So, to first order in omega and epsilon, I will have a linear combination of the omegas with a bunch of operators and epsilon, the sum operator. So, what we do is write this down as I by 2 omega mu nu j mu nu minus I epsilon mu p mu. Plus, of course, higher order terms, but I am right now concerned only about the linear order term. Now, in case you are wondering about the signs involved, you have a plus sign here and a minus sign here. The reason why you have that is simply to make these operators j mu nu and p mu match with other operators that we already know from non-relativistic quantum mechanics. So basically the signs are more for convenience, just to ensure that these operators match with operators we already know and love. What about the half in the I by 2 omega mu nu j mu nu? That actually is simply to ensure that you are not actually double counting things. Notice that omega mu nu j mu nu will have omega 01 j01. It will also have omega 10 j10 plus, of course, other terms with other values of mu and nu. Now, omega 01 and omega 10, as we have already seen, are negatives of each other. So, this thing is really omega 01 j01 minus j10. Now, note that in this case, if j01 had a part which is symmetric, in general j mu nu had a part which is symmetric under the interchange of mu and nu, that would simply cancel out here. When you subtract j10 from j01, the part which is symmetric under the interchange would have simply dropped out. And since the only place where j mu nu's occur basically is this equation, you can see that any part in j mu nu which is symmetric under the interchange of mu and nu will never show up in practice because it's always going to drop out. Hence, what we always do is assume that j mu nu is antisymmetric under the interchange of mu and nu. So, j mu nu is always minus j nu mu. But if you use that, then notice that this is going to come out to be twice omega 01 j01. Plus, of course, the other terms in the sum. Note that omega mu nu's, although there are 16 in number, the 4 diagonals we already know are 0. And the 12 off diagonals, all of them will actually come in this sum. But each of the off diagonals terms will come twice. Like omega 01 came twice. Once with j01, the other time it's minus j10. A similar thing is going to happen to every one of the off diagonal omegas. So we'll essentially end up with the independent omegas times their corresponding j's multiplied by 2. The half in the definition simply cancels that out. So that ultimately, if you expand this whole thing out, what you are going to get is something like I times omega 01 j01 plus omega 02 j02 plus omega 03 j03 plus omega 12 j12 plus omega 23 j23 plus omega 31 j31. Each of these terms actually came twice, so they had a factor of 2, and that is being cancelled by the 2 here. That's the reason why you have a half. In addition to the demand that j mu nu is minus j nu mu, the other property which these operators, j mu nu, and in fact also the p mu's, must have is something we have already seen before. For u to be unitary, we need these operators here to be purely Hermitian. Remember, that is exactly why we have the i's in the front. Because of the i's, you end up with Hermitian matrices for j's and p's. If the i's had not been there, j and p would have ended up being anti-Hermitian. Because in quantum mechanics, we like Hermitian operators and we can relate them directly to observables, we have put in the extra I. By the way, when mathematicians talk about Lie algebras as things which come from Lie groups by expanding about the origin, very often they don't include the I. And they live with anti-Hermitian operators. After all, to a mathematician, an anti-Hermitian operator is a structure just like a Hermitian operator is. It is we physicists who have a special affinity towards Hermitian operators, because Hermitian operators, after all, are what gives us observables. But be that as it may, both J and P here are Hermitian operators. So this is an important property which we have to keep in mind. To give the game away a bit, the operators P1, P2, P3 which we meet here will turn out to be components of the momentum operator. J12, J23 and J31 will turn out to be the angular momentum components J3, J1 and J2. So again, a familiar operator from non-relativistic quantum mechanics. And P0 is actually the Hamiltonian. J01, J02, J03 are actually generators of boosts, which are intrinsically relativistic, so we don't really meet those in non-relativistic quantum mechanics.